So hello everyone. In the previous session, we had started discussion on k-nearest neighbor algorithm. So in that, if I just revise you a bit, what k-nearest neighbor algorithm was. So in that, we were assuming that the similar points have similar labels. If a point is living in the vicinity of other points, so we'll consider that the point in the what are the points in the vicinity are. We'll consider that label for the point. So we took an example even. So here this k was the number of nearest neighbors. The number of nearest neighbors. Okay, so in that what we saw is we saw steps in the algorithm. The first step was if somebody gives us this k, we call it an hyperparameter. We said it is an hyperparameter, we have to set it. The k usually we said put it odd number because there then majority vote won't be a problem for us. So the first step was compute the distance. Compute the distance of k nearest neighbors. The second step in there was do the majority vote. So when you compute the distance to the k nearest neighbors, you'll get some distance, and correspondingly you'll get the labels. So you'll get the, for example, if we have 3, so if corresponding label was positive, 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 that's plus labels because we had 2 classes. The running example we had was email spam. That was the example we had, and we are given a bunch of emails and their corresponding labels. So if all the labels were this means not spam and negative means spam. So if this was plus plus, they will say the point query point that we have queried, we'll call it a positive point, we'll call it no spam email. Okay, and that's what majority vote will do. And in that we start with what the definition of neighbors, how to compute the neighbors. So we said, like even Amir and you guys said that when you compute the neighbor, by definition neighbor means which is nearest. So I said how to compute the nearness or closeness or maybe distance. Then we had different types of distance. We started with a lot of distances, like we started with Euclidean distance, then we started with Manhattan distance, Minsk-Korsakoff distance, and then I think we also saw Hamming distance. So some more distances I'll just cover, and so that I told you there are at least like 15 plus which I know. So some distances which are frequently used, I'm just giving you those distances. And there is a distance called as Chebyshev distance. Chebyshev distance. So what it says is, it says, for example, let's suppose we have 2 points. I'm just talking about 2 features. We have this x1 point and we have, let's suppose, this x2 point. So here, this is the first feature. Let's call it x11. That's the first feature of the x1 point. And this over here is x12, second feature of the first point. And similarly, let's make this point a little bit here. So here, the first feature we'll call it x21, that is the first feature of the second point, and for this we'll call it x22. If somebody wants to compute this distance, so what we do is we basically will take this distance or this and take max of these, whichever is maximum of the distance, we'll call it a distance. So x1, as you know, is now x11, x12. This is the coordinates, this is the features in the point, and then we have x2, that is x21, x22. And what is the Chebyshev distance? It says compute this and compute this and see the maximum distance among these. So if you let's denote it by C, Chebyshev distance CT, that's equal to maximum of, let's suppose, this distance. This distance is the first component, the x first component minus x1 of first component. So we'll take its absolute value, comma, absolute value of x22 minus x12. So whichever is the maximum, we'll consider that as the distance. This is one of the distances. Okay. So other distance that we use is, like, now I'll shift to similarities also. So because many of the times I have seen similarities also come in the picture when you compute the distances. So what is the relation between similarity and the distance? First, I'll take that relationship between similarity and the distance. Because that's how, like, implicitly we're again making some assumptions. We were saying that for example, if we want to compute neighbors will have less distance. That's the thing over here. So if we talk about similarity, more the similarity, less the distance will be. So they have this inverse proportionality. So if I say that similarity is very high, then distance between points should be very less. That's the definition of neighbors. So if you talk about what is a neighbor, neighbor should be close to you. That means it should be similar to you. So if we compute anything mathematically, so what should happen is, so similarity should be defined in such a way so that distance between these points is very less. If we have two spam emails, let's suppose only these are two features, feature 1 and feature 2. So if a spam email is right here, and other spam email is very similar to this, and it is a spam email, then it should have very less distance. So other spam email, let's suppose, should be here. So if a point is, say, here, so it is very far away from these 2 points, that means this should be no spam email. So that's what I mean. If there are similar points, they should have very less distance. So I'll write it here. So similarity is inversely proportional to distance. Meaning is that if the similarity increases, the distance should decrease. Up arrow means increases, and down arrow means decreases. Is the relationship between similarity and distance clear?
Yes, sir.
Now, as you are seeing that when we were talking about distance, we saw equivalent distance and we saw many other things. But distance can be measured in other ways as well. So we can also include the information of angles. So what is the first? I'll tell you the problems with this. Problems with above mentioned approaches. Mentioned approach. Let's suppose now we have a point, we have this, and then we have a higher dimensional data. If we have lot of dimensions in that, then we need to compute this. Let's suppose this roots and stuff like that. If we want to compute Euclidean distance, so if a point x belongs to, let's suppose, rd, and d is very high, and then we need to also compute the square root of these things. So a lot of computation is involved in that. So as you know that we have to first take the first component of the first point, and then subtract it by the first component of the second point, and then take the square of this and keep on doing, and at the end take under root. It will be a huge computation. So if we have a lot number of points and we want to compute distance, so there is something called as cosine similarity and cosine distance. This is an interesting topic. Cosine similarity and cosine distance. Do not get over that bigger picture. Do not lose that picture. Actually, what we are actually trying to understand these two steps, how to mathematically understand them. Now we don't know the intuition about the algorithm. The feathers of the same flock, something, that quote which I said, birds of the same feather flock together. If there are birds which are like from the same category, they'll fly together. That is the same thing over here, the assumption with the data set. If we have a data which is in which the neighbors are of some class, so that data point is having the high probability of being in that class. That's what we're trying to understand. Now we're sort of capturing the definition of a neighbor, or definition of what is the distance and similarity. So now what is the meaning of this cosine distance? So giving you upfront the formula first. So cosine similarity, so 1 minus cosine similarity of points between, let's say, x1 and x2 is equal to cosine distance. Cosine distance of x1, x2. So what is this? So as I said, that these are inversely proportional. So that means, for example, if this cosine similarity, let's suppose, has a range of -1 to 1. Okay. So here, if the value is 1, that's 1 minus 1 is 0. That cosine distance will be 0. So 1 means high similarity, let's suppose. Okay. Or even we can say 1 means, let's suppose, high similarity. Or even we can say same thing for this cosine similarity, it may belong to 1 minus 1 comma 1. So what I'm saying is, so if you put a value, or if you put higher value over here, you will get a lower value over here. For example, we put 1, so we'll get 0 over this. So if you put, let's suppose, -1, so you'll get 2. You saw that you saw this distribution. If you even put 0 over here, then you will get 1. So you are seeing, for example, the first you had 1, you saw this is 0. Then let's suppose I'll write in the order. So I'll write 1, 0, and -1. So here you will get the answers as 0, and then I'll write this will be 1 and this will be 2. So as this sort of decreased, you are seeing this increased. So that's what I mean by that. This inversely proportional to each other. So that is cosine similarity and cosine distance. So this is the formula for that. Now we'll define one of these quantities and we'll quantify them. Okay, so let's suppose we have again these 2 points, x1 and x2. This is my x1 and this is my x2, let's suppose. Now what we are saying in equivalent distances, we are trying to calculate this d, the equivalent distance between that. So now the distance can be measured in other ways also. For example, if I consider this theta, so I'll say what is the angle between these two. So if I know the angle between these two, then I can capture some sort of similarity between these things. So what I'll say is, I'll say cosine similarity of x1 comma x2 is equal to cos of theta, and this theta is the angle between x1 x2. So this is how I define this cosine similarity. So I define cosine similarity as theta angle, cos of theta, and theta is the angle between x1 and x2. Okay, so if I say you, if I have a point, for example x1 over here, and then there is a point x2 over here, this is x1 and this is x2. Now you see there is a small angle between them. Or let's suppose we'll take, even if there is a point x2 onto this, so then angle between this is 0. So then the similarity is 1. So 1 means the highest similarity. So that's what I was saying here. So 1 means the highest similarity. So then what's the distance? Distance between them should be 0. Then that's why here you'll say 1 minus 1, that is 0. So 0 similarity of similarity of 1 means like they are very highly similar, highly similar. And distance of 0 means they are similar, the same thing. That's what we are capturing here. So we are just capturing the angle between these two, and there is you can see even there are problems. Or you can see this, for example, if we have this point, we have a point x1 over here, then we have a point x2 over here. So this x1 and this x2 lies on the same line. If you see it, angle between these is similar. So cosine similarity says that both of these points are similar. So that, like, there are applications of this distance when you will learn about deep learning and other stuff, and we'll see that sometimes we want, if 2 points lie on a similar line, we'll call them similar. So for in that applications, this becomes really important. Is it clear? Is the cosine similarity and cosine distance clear?
Yes, sir.
Okay, let's again take some graphical example so that you will understand it better. So now let's suppose we have this is our 4 quadrants. If I have a point over here, okay, if I have a point over here, let's call it point x1. Okay, so I'll also make the quadrant parallelly. So I'll have the first quadrant, second quadrant, third and fourth. These are my 4 quadrants, and I'll see what happens to the similarity and what happens to distance. Again, knowing the formula, cosine similarity of x1 comma x2 is equal to cos of theta, and this theta is the angle between x1 and x2. This is the definition of cosine similarity. And 1 minus cosine similarity of x1 and comma x2, this is equal to the cosine distance of x1 x2. Just remember these things. This is how we define them. Okay, so now I'm saying if there is this point x1, so now if I have point x2, so if I have some point x2, now let's call this point x2 over here. So x2 is this point. Now the angle between them is 0. So if the angle between them is 0, that means they have a similarity score of 1, because cos 0 is equal to 1. Okay, so now if this point, if this started moving from here to here, this point x2, so now if x2 is, let's suppose, here, okay, so now you saw that the angle got changed. This angle got changed now. This became orthogonal or 90-degree angle. So when in the first quadrant, first the similarity went from 1, then when it went here, so it went from 1 to 0 in the first quadrant, if you see it. So here the value was 1, similarity score was 1, and here the similarity score became 0 now. And now you again take, if you take x2 over here, so this will be cos of 180 degree, not even 180, sorry. So if is it 180, 90, it's 180. Yes. So if you see, this is 90, 90 is 180, so it will shift to 0 to -1. So it will become again more dissimilar. So once it started from here, it started going towards dissimilarity, less similarities between them. So when it comes back, it has become more similar, because the angle between these two is now sort of becoming less. So now if it goes from this in the third quadrant to x2, let's suppose x4, this again x2, and it's going to fourth quadrant. So now you see the value over here will again be 0. So it will go to -1 to 0. Okay, similarity will basically increase now. So again, if it goes in the fourth quadrant from x2 to again this in the first quadrant, so the value will become from 0 to 1. So it will become exactly similar. So are you seeing this? Like when I'm taking the similarity, I just say the theta between these. So when it goes from here to here, initially it started increasing. In the first, it started increasing. In the first two quadrants, the similarity they become more dissimilar. So after that, when they come back to the first quadrant, you see the similarity again increase and it goes back to 1. The distance, accordingly the things will happen. So when it was x1 was here and x2 was also there, so distance between them was 1 minus cosine similarity. That's 1 minus 1. The distance between them was 0, because at the end you can see it over here, they are on top of each other, so the distance between them was 0. So it went from 0 to, then when it went from this 0 to 1. Okay, so I'll write this. So here the distance was 0. Okay, here the distance was 1. Now when we again go here, the value of cos theta became minus 1. Now 1 minus 1 minus 1 is 2, so the distance will become 2. This is the maximum far apart they can be. Okay, one is on the one side and another is on totally flipped side. This is 2, and when it comes back, so it will again become 1 over here. Okay, so it first went from 0 to 1, and then it went from 1 to 2. Okay, then it went from 2 to 1, then it again went from 1 to 0 back. This is the distance, and you can see this quadrant, in the second quadrant at the end, they become pretty much dissimilar. So here x1 and x2, they become dissimilar. The both is shown by similarity as well as distance. Okay, now you can capture the cos theta. You know how to capture this cos theta. So we have been doing this all along the algebra. So you know, if given x1 comma x2, if you want to find the angle between these things, so we'll say cos theta is equal to x1 dot x2. We'll take dot product of these two things, and then normalize them and take the norm of this x1 and x2. We'll take norm of these. Okay, so if they are unit vectors, we can directly say cos theta is dot product x1 dot x2, or in the matrix notation we can directly say x1 transpose x2. We have been doing this all the way along. So there is again a relationship between Euclidean distance and this cost, basically cosine similarity. So you can find that online, so it's easy to prove. Even let's suppose, as you know, that if we have a minus b, so if we have, this is let's suppose our a, this is let's suppose our b, this is our Euclidean distance. So you know that we can make a right angle triangle over there. So the thing that we have been doing so far there. So this is a, let's suppose this is b, something like this. And then if we want to find the distance, so what we actually try to do is we'll get the triangle, if you remember the first lecture. So in that, this will be our d that we have to find, and this will be the square. So d square will be this square plus this square. So I think you remember this figure. So I have made it, I think, today also, no? Here. So if you see the distance between this, so this is the distance that we are capturing in Euclidean distance. Okay, so this square plus this square is basically this square. So that's what I'm saying, a minus b whole square. So in the terms of algebra, I can write it like this. I can write it a minus b transpose into a minus b, the way I wrote it here. So x1 dot x2 is, you can write it like x1 transpose x2. That's what I did here. So now you can just expand it. So you will get a square plus b square plus 2a transpose b. Okay, now let's suppose these a and b are unit vector. So if we consider these a square and b square, they are unit vectors. So here this will become 1, this will become 1. So this will be equal to 2 plus 2a transpose b. So we're assuming that these a and b is a unit vector. A and b are unit vectors. Okay, now what it boils down to, this is, so this is actually minus, this should be minus, not plus, because this is a minus b whole square. So now we can take this 2 out. So this is 2 1 minus a transpose b. So now you know that if the unit vectors are unit, so this is actually cos theta. So I can write 2 into 1 minus cos theta, and theta is the angle between a and b. So you know what is cos theta? Cos theta is cosine similarity. So I can write it 2 into 1 minus cosine similarity between a and b. And you know what is 1 minus cosine? That's cosine distance. So I can write 2 into 1 cosine distance. Is it clear? This is a simple relationship between Euclidean distance and this cosine similarity. Is it clear?
Yes, sir.
Okay. So now this is again a format of describing this distance and similarity by using some other metrics. So there are other lot of distance. I'll just mention few of them. So if you had time, you can just explore them on your own. There is something called as Jacquard's distance. Jacquard distance. Okay, I'll just name the famous ones which you will use some way. And then there is something called as Mahelonton distance. So I won't define these things for you. I'll just like name them so that I can just research them about a bit. So then there is correlation based distance. Oh, there is correlation based distance. Then the famous distance that is used there in deep learning is called Earth movers distance. Okay, and there are a lot of others. So I just named few of them. Now we are done with this. So now we are done with at least quantifying how to measure distance. So now we need to see how to make this algorithm, how to work with the algorithm. So we know the how to compute distance now in the k nearest neighbor. Then we know how to even do majority vote. Now we have all the pieces in the algorithm. So we need to take this algorithm and then we need to implement, let's suppose in our language Python, or first we need to develop a pseudo code, how to write the code for it, then probably we'll transfer it to the like Python, will translate it to Python. So let's consider again reiterating this. Let's suppose we have a data set in which we have spam emails. We have emails, we are given emails, and we have to detect whether email is a spam or not spam. This is a binary classification problem. So what will be given? You will be given emails, a bunch of emails with it. Let's say thousands of emails will begin, and corresponding there will be labels also. So how to construct data set that you are experts by now, because you have done a lot of assignments just because how to gather data. So it will be a matrix which we call as data matrix. So in which each the row, let's suppose xi transpose. So this, if I take this xi throw of this, so this will be ith email. Why I write transpose? Because you know that we normally write every vector as a column vector. So if you have to fit in the data matrix, we just transpose it. So this is one email. So this xi transpose is an email, and correspondingly we have the yi its label. Okay, that's the label we have. Let's suppose 0 for no spam, 1 for spam, something like this. Okay, so this is our data set running example that we are doing. So problem is, so let me again write it. So problem is, given a new email, we have to label it. We have to label it as spam or no spam. That is the job, because even when you receive the mails on Gmail, some emails will directly go to spam folder, because that email might have the contents based on which it is saying it's a spam email. That's the problem we are given. So now the thing is, if we have this data, how to train, how to test our model, and then how to mathematically sort of get this thing into KNN, and then how to code the algorithm. Because now we have every tool that is possible, that is needed for this KNN algorithm. So now we have this data matrix. Let's call this DN. Let's suppose, because let's suppose it has n samples, so we'll call it DN. Okay, DN is our data matrix. So what we have to do is, now we have this whole data DN like this. Let's suppose this is our DN. The first thing will do is we'll try to break or split the data into such a way so that we have something for the training and something for the testing. Okay, so we'll have, this is the train, this is our d test. This again, how to split it is a huge topic, as I said. Like we'll deal it with separately, so we'll take a separate session on these, probably like how to split the data, what is the ratio that usually people take. Point 0.8 here, they like 0.8, and here they like 0.2, something like that. But what's the reason behind that, and what is different types of splitting, maybe we'll take a separate session on that. But here just know that we first have to train, and then we'll test on something. Let's say we have n1 points over here and we have n2 points over here. So n is the total number of points, so n1 plus n2 should be n. So this is our train points and this is our test points. Okay, so what we'll do is, you will take each point from this test. Okay, then you will query it in the train, and then we will see what's the label of KNN. Okay, so again, how to some things I would like to say about this dtrain and dtest. So d and total data should be union of these two, dtrain union dtest, and there should not be any overlap. So dtrain intersection dtest should be 5. So this means no duplicates. or no repeating points. Like whatever point is detrained, it should not be in the detail. Otherwise, it does not serve the purpose. So our point is that if we train a model based on something, so when we test, the test should be sort of unseen for us. So we should not see the test. That's what I call generalization. I said generalization in the previous lecture. So even I gave an example about Nokia phones. So when they trained the model, they trained it on European people, but when the model was deployed in the real world, what happened? So it was not detecting many people because the distribution the people they had were from the, like they had different facial features. Okay, so that's the reason we should have like the sample should represent the distribution. That's the first thing. The sample that you are taking to train the data, it should be actually representing the whole distribution. And the second point is when you test even, so when you test it should not overlap. And I think I also said you that example. So there was a classifier which claimed that 100% accuracy on spam data. So what they actually did is, so each email was repeating. So each email was repeating multiple times when they were splitting the data. So there were duplicates in train. So they were training the classifier and they were testing. When it was tested, it was giving 100% accuracy. Why? Because everything that was there in the test, that was also being trained on. The algorithm was basically trained on the same things which the test had. It had some repeating values. That's what I'm saying. So it should be well generalized. Your algorithm should generalize the things well. It should see the data which it has never seen and give some accurate results and give some results which are at least like acceptable in the real world. Okay, that's why like you have to remove these duplicates and do this stuff. Now what will we do is, so now we split that. Now we are in the formation how to form this algorithm. Now we have tools how to use these tools and do the generalization. So what I'll say is I'll tell you to take this dtrain. Okay, now we have this dtrain. Okay, so consider it as trained because there is no training step involved in our KNN algorithm. So because there is an assumption, so that neighboring points, whatever a point is neighbored by some points, so that will have the same label as the neighbors. That's the assumption in here. So there is no such training involved. But in algorithms like SVM, you'll see neural networks, you will see the other, they have training steps involved. So there we'll have to train it on the data. But here we'll consider training is like this. Let's suppose we have these emails, let's suppose which are not spam, and we have these red emails which are spam. Okay, now we have d test also, so we have some d test. Now in the d test what we have to do is we'll have some points, so we'll take each point from the d test and then we'll, let's suppose this is our query point. So here I'll query, this is our point, and I'll take this as query and I'll query it here over here, and I'll compute the neighbors whatsoever k I have given. For example, k is 3, I'll compute the 3 nearest neighbors. Then if majority of these neighbors are of a certain type, I'll give this point as basically that type. I'll say d test is of that type because the most neighbors are of no spam, so it's a no spam. Or if most of the neighbors, if I take this over here and I say 3NN, so I'll compute the distance with the 3 neighbors and see these 3 neighbors have basically no spam. They are spam emails. That means this email is also a spam email. Okay, so now I'll write a pseudo code for this. But first we'll see the simple implementation, vanilla implementation. Is it all right till here? Have you understood everything? We have some data and we have split it into d test and d train, and this split is, as of now, we'll do it randomly. But I said this is a huge topic on its own, how to split, and there is something called as time based splitting and other things like that. So but here let's take it as a random splitting. We'll randomly split the data. Is it clear?
Yes, sir.
Nice. Okay, maybe parallelly I'll also code so that you get to know. I'll generate some data and then I'll show you the steps that we are doing. So I'll parallelly show you that. Let me go to the code window. Yes. So what I'm saying is that we'll now move to the simple implementation of KNN. So why is it called simple? Because there are other implementations which we'll do in near future. So far what we have done is we have a data set, and then for that we have this dtrain and dtest. Okay, so the input of the algorithm is dtrain, the training set that we have, the k hyperparameter, and this xq, the query point that we have. This is the point for which we want to find the label. This is our point for which we want to. Let's suppose in our case it's an email. Somebody gives us an email So he or she tells us, is it a spam or not? So we'll have to give a label as output. So this is our output. Output should be the corresponding label. So what I'm telling you is, so for each of this data a point in the training set, so there will be here in our example we have 80 points in our data detrain. So if somebody gives me this xq, so what I'll do is, the first step in that is, I'll compute the distance of this xq with every point that's in detrain. Okay, for each xi in detrain, that means take every point in detrain and compute the distance of the xq of this query point with the xi, with every point in detrain. Okay, this is the first step that I have to do. And then what I have to do is, now I'll get, how many distance will I get? Any answers? So how many distance will I get? Because detrain has n1 number of points, so I'll get n1 distances. So here I'll get n1 distances. So these many distances I'll get. Okay. So then the second step is that, now keep the smallest k distances. Now you'll have to sort it in some way so that you get top least k distances. Least k distances. Now you have n1 distances. Now you have to sort them in some way, and then you have to get the least k distances, because this is k nearest neighbor algorithm. Okay, and then you'll get something like this. Let's suppose you will initiate a list of neighbors. So in that you will get some points like this. You'll get xi, comma yi, and di. Okay, this will be, and this will go on. This will be a list. Now you have only, let's suppose we have 3 NN. So you will take the top least three distances, three neighbors which have least three distances. And then the next step is that, next step will be to do the majority vote. Do the majority vote, and then when you do the majority vote, here you will get the label. This will be the output. Is the algorithm clear? Tell me, is the algorithm clear?
Yes,
Is,
sir.
okay. So how to do majority vote, you know now. For example, in our case we have two classes. So let me again expand on this, how to do this majority vote. So you will say uh, number of positive points. Let's suppose number of positive points pp is equal to 0, and number of negative points np is also equal to 0 in the initial say. This is also 0. So what I'll do, you will say for, okay, for the points here, you'll compute this di. For di in whatever the set is, this will be nearest neighbor set near nn. For di in nn, okay, compute the label. So if di is, let's suppose if di is equal to 0, then 0 means no spam. So 0 means no spam. So you will increment this. You will say number of positive points, or maybe positive emails, number of, let's suppose, negative points np, that you will plus it by 1. And otherwise, so if this is equal to 0, else if di is equal to 1, so then you will increment this positive point. Number of positive basically means spam emails, plus is equal to 1. So this is the majority vote. Then you will compare which of these are greater. So if number of pp is greater than number of np, basically among the points, you will see which are these, which were like neighbors in the neighboring points, what was the label that was prominent. So you will say, if this is greater, this positive points, I'll say pp. If positive points were greater than negative points in the neighboring, so you will say the point that we have is a positive point, else it was a negative point. Okay, that's the first thing. So here we compute the distance. Okay, then we saw only got the top least k distances. So you'll take the least k distances, and there'll be k points, and correspondingly we'll have corresponding d to them, and then you'll do a majority vote, and this is how you'll do the majority vote. So how many of you are clear with the KNN algorithm now? Otherwise I can again reiterate it
Yes, sir.
once. Is it clear? I can.
Yes, sir. Yes, sir.
Okay, nice. So now we'll code it, and we'll code this algorithm stepwise again, and what we'll do is, we'll go through the steps in the code, and we'll write the code for it. Okay, is that all right?
Yes, sir.
Wait. So here we'll see the stepwise implementation. The first step, if you see, was this: for each xi and d train, you have to compute the distance, and you will get a query point, and you have to compute the distance. So what am I saying is, so you have to implement this algorithm according to these steps. So we'll be using object oriented code. So we'll make a class of KNN first. So I'll go to the coding window and show you the code. So here it is. The first thing that you will see is here we have imported numpy, and then we have imported this collections because we want to count something, because in the majority vote we need this counter. So if you see over here, I made a class KNN. Okay, I won't explain what class means because we'll take some separate sections on what these classes and things are. But as you know that there are functions, you know the functionality, what functions do. So what I'll do is I here the k is equal to 3. This is the default value of k. Okay, so this is the default value. If somebody wants to overwrite it, he'll first make an object of this KNN. So he'll say, let's suppose k nearest neighbors. So he'll say k nearest neighbors is equal to KNN of 4. So this 4 is a have parameter. So we'll make an object like this. So this is the class. So here we have this self.k is equal to k. Then we'll write a function fit function. So fit basically means it'll train the classifier. Now you know that here we have no training. So we'll just give this x as training data and y as this training labels. And then there is this function predict. So this will do the whole job. So if you see what we do, what we did in the step 1. So we'll get a query point here. If you see, we'll get a query point for each of this. We'll compute the distances. Okay, then take the top k distances. That's what this predict function will do. So if you see it over here, so what it'll do is it'll say for x in x test. Okay, because it's now taking first point from the x. Let's suppose it is taking first point. Let's suppose for the first x. Okay, so what it is doing, it's calling the self.predict. So this is a predict function that we have written. This is the predict function. So what it does is, let's suppose it takes the first point in this x test. So what it'll do is it'll compute the distances. Distance, how will it compute this? It's usually equivalent distances. It will compute the norm x minus x train. Every point that is there in x train, it will compute the distances. So here, how many distances will be computed in our case? If you are following the algorithm, how many distances will there be? Because we have dn is equal to 100 points. So we have 100 points in total. So d train we have is equal to 80 points, and d test is on 20 points. So now we just chose the first point from the d test, and now we are computing that point distance with every point that is there in d train. That is what this does. So this is saying compute the distance. So if you know, this is a norm, basically equivalent distance is computing the norm. So this is a list comprehension that we have went through. So this is saying compute this for this x train, for each of this x train, because this is the point that we are getting as input, and compute this distance for the every point. So here this will be the will compute 80 distances. Okay, is it clear?
Yes, sir.
For the 80 points, then then what we do is we'll sort these distances. So I have also said what's the meaning of arg min and arg max. So here this is arg sort. So this will get me the indices of these points which are having the least distances. Okay, so this will give me indices of these. So what I'll do is then, so I'll say what are the labels of these things. So this is the first step, computing distances, and then getting those three points, getting the 3 points which are least distance. Okay, now I'll get their labels. Okay, I'll get their labels. That's what I'm saying. Most common, whatever label they have, and then I'm doing a majority vote over here, and then I'm returning that most common vote. If you see this majority vote, again going back to the going back to what we have seen so far in the theory and that we have seen in the code, so that it matches. This is the first thing we did. So we took a point xi. This belongs to train. So this belongs to train data. So then we computed distance of this training point with every distance of this test point. Sorry, with every training point. So this is our testing point. So this belongs to test. So we'll take this test point, and now we have to compute the distance of this point with respect to each of the points in D train. That's what we are doing. Compute the distance xq xi for all of these points. So that what will happen is, so it will, for in our case, it will compute 80 distances. Then second thing is, we are taking the least k distances. So we are taking the topmost least k distances, and then we are doing the majority vote on them. So that's what we have done in the code. So if you again see in the code, so the first thing that we have here is compute the distances. So then take the top k least distances, okay, and then get their labels, and then do the majority vote, and then return that majority vote. Okay, and this will be done for each point. That's why you see a for loop in the predict also, because this is done for each of the point in the test. So this will be done, this loop will run 20 times. So this will run 20 times. Okay, so this here there is this loop will run 80 times, because we're comparing the distance with 80 points. So here this k label, so as we have 3, this loop will run 3 times. Okay, now because the k is 3. and then we'll get the most of this. We'll get basically the majority vote. We'll get the label, corresponding label of these points, and these points we're storing, like most will store it somewhere. Is the algorithm clear so far?
Yes, sir.
Maybe I have written the code in really very succinct way. This is like sort of a code. If you write it, maybe you won't, you will not use the list comprehensions, but try to use these comprehensions. Like otherwise, you can just compute the distance by some other function, and you can add them in the list. This is the like succinct version of the code. I think you understood the code. Can I assume you understood the code?
Yes, sir. Yes, sir.
Sir.
Zubair, Rian, have you understood?
Yes, sir.
Nice. So now I'll run this algorithm. So I'll again here. So I am calling this KNN as by KNN k is equal to 3. I am giving the hyperparameter k is equal to 3. Then I am saying KNN dot fit. Actually this fit function does nothing. So if you see it over here, fit function it just initializes this x10 and x test. Okay. But now you saw that because we in the previous I think this box we have generated this train data and test data, and you can clearly see I am just calling a function fit. It will just assign this x train and y train to the x train and y train corresponding. Then I am calling this predict function for each of the points. So what I am saying is I am saying for x test call this predict function. Okay, so this will internally call this function, and this will give me the this will compute basically. I don't want accuracy right now. This will give me predictions. So if I run the predictions, you can see it over here. First is predicted as not spam, spam, not spam, not spam, spam, something like this, till this. Is it clear?
Yes, sir.
Now I want to compute accuracy. You know how to compute accuracy. So now I need to compute accuracy. Accuracy is one of the measures how we compute this. This is also like 1 minus binary loss function, because now I have an algorithm which says me is the spam or is it a not spam. So how to compute accuracy? Now we have n2 number of test points. This is number of test points. This is my number of test points. Total points is n1 n1 plus n2 is the total points. N1 plus n2, which we call as n. This is total number of points. Total number of points. Okay. So if I need to see the accuracy, now what I'll see is I'll say among the test points we have, we had n2 points, and how many were correctly labeled. Okay. Let's suppose that correctly labeled points were n dash. So n dash here is number of like correct predictions. Correct predictions. Okay, in our case you will see that it will get 100% accuracy, because on purpose I have made these clusters so that it does it follows the assumption. That's why you see the clusters are separate. So here you will see, if you compute the accuracy, what we have to do is you will say the number of test points that we have and the number of the correct predictions. Okay, how will you compute these correct predictions? You will see whatever has been predicted, and you will compare it with the actual label. What was the actual label? Actual label are present in y, and predicted label is present in the predictions if you see in the code. And then you will compare these, and then you will take mean of those. So again, going to the code, you will see it over here. So if you have to see how to compute accuracy, so what I am doing is I am saying predictions over here. Predictions is equal to y test. Like compare these predictions and y test. Y test is the actual label. So this over here. So this over here, if you see it, this is my actual. Am I audible?
Yes, sir.
Is the screen
Yes,
visible
sir.
also?
Yes, sir.
Yes.
Nice. So what I'm saying, this is the actual labels. This is my actual labels, and this over here are my predictions. These are my predictions. So what I'm saying is it will compare the predictions with the y test, and for wherever it got it true, it will sum them up and average it. So here, if you see, this accuracy will be 100%. If I run this cell and print the accuracy, so I'll just print out this accuracy. So you'll see this is 1.0. That's 100%. Is it clear?
Yes, sir.
Nice. So this is the vanilla implementation of this k nearest neighbor algorithm. So now let me take you to some real world situation where we'll see the time and space complexity of this algorithm, let's suppose, because you'll have to implement this algorithm if you are working in Google and you are given a task of separating this emails spam and non-spam, labeling these spam emails. So we'll see how much time will it take. Let's suppose each email that belongs xi belongs to an RD. It has D features. Each email will be basically a bunch of tokens, and let's suppose it lies in the D-dimensional vector space. Okay, so if you see this matrix, let's suppose we have in the D train, let's say we have 500 million emails. Okay, it's a realistic number, and even I think we will have more than this. Let's suppose we have 5 million, 5 million of these emails which are there in, let's suppose in test, and this is an n, and let's suppose D is somewhere around 100,000 million. Not let's suppose k, not million. We'll write k. 500k and 100k. This is our D, and let's suppose this is our n, and this is number of emails. Number of emails we have, and this is a number of dimensions, number of features basically we have. Based on these, we'll do our analysis. So what is time complex analysis? We'll see how much time and how much space will it take. If you see this step, okay, if you see, for example, this for loop, how many times will it run? It will run for a D train number of times. How many points are there in D train? And computing distance, it will depend on D. So this step will run order D times, because it will have to do D computations, those subtractions and squaring them up, then at the end taking an under root for the equivalent distances. Computing norm, each of this will take order D. How many of you understood this step? Like this will take order D time.
Yes, sir.
This will take order D time. Now, keeping the case summarization, maybe there are algorithms where you can do it in order 1. So because you'll parallelly do it, you'll just keep 3 nodes by which you can just take the least like k distances. You'll just keep a track, and if it replace the previous 3, so you can do that. And here also majority vote. Like basically it is in order. How many, for example, this is order 1 again, because k is very low. We generally consider k is very, very less. That's why I'm saying order n. If the k is in terms of, let's say, hundreds and thousands, then we'll have to take k also. So but k generally is 3, 4, 5, 6, 12. So again, is this number, if you see this 500k, the k is very, very less. This k is very, very less. That's why I'll consider this majority vote also as order 1. Okay, because you'll have to do majority vote on maybe for example 12 points. And if you see how many times this loop runs, it will run order n times, because there's a number of points we have. So total complexity, if you see, is order nd. So total complexity is order nd. I'm just ignoring those order 1 terms. Okay, so this is the total time complexity. This is how much time it will take. So just giving you some notion how much time it will take is, so if we have this 500k and this is 100k, so this will be 50,000. kk is million, so this is 50,000 million. Let's suppose this is the time it will take. Let's suppose each of this operation takes 1 millisecond. So these many number of milliseconds will it take. So it's a huge time. Okay, even in the space complex, if you see space complexity, if you ask me how to compute space complexity, usually the complex space complexity, when it's computed, that time we don't consider the input, but here we have to consider input also. This retrain, it has to be present in the RAM always, because you are querying a point, and the data trained data must be present in the RAM, otherwise you cannot retrieve the results. So this order nd, this number of points and dimension, this much is also space is required. Okay, so how much space is this? So this is nearly like this m million, and you can just take these. This is nearly 50 GBs. I'm saying roughly 50 GBs you'll have to have in the RAM if you apply the the algorithm that you implemented. The algorithm that we saw, simple implementation, it will require 50 GBs of RAM. So how many RAM it will require? How much RAM it will require? It will require 50 GBs of RAM, and then even the time will be very high. For one email spam, it will probably take more than like 1 hour or so, greater than this time. Like by computing, if you just adjust these, and then you will see how many seconds will it take, divide that by like 3600, and you will get the number of hours it will take. So do you even feel that this is realistic? Like for example, if you are working in a Gmail office, and then they are telling you to label the email as spam and non-spam, then you are telling me first give me 50 GB RAM, and then that system I'll do this KNN on, and then before sending a mail, I'll check it for 1 hour, and then I'll send it to the user. I'll say whether it's a spam or not spam. So will you do, like, is this realistic?
No, sir.
This is not realistic, because email stuff is, we call them low latency systems. So low latency systems means like where latency should be very less. It should be almost instantaneous. For example, this is a low latency system, email stuff, and then we have markets. Let's suppose we have forex market. So if you are making any trades on forex market, again it should be a low latency system. So this implementation is not realistic, but you understood the implementation. Now we'll see something called as, we'll use kd trees, and we'll use also something called lsh. These concepts will be used to implement the KNN to make it better. Okay, and by the help of which we can decrease this complexity. That's the reason you won't see majority of the people using KNN, because it uses a huge amount of space, and it also uses a lot of time when you are running it. So many other people will ignore this algorithm. Maybe it is so elegant, so simple algorithm, but the thing is, it takes a lot of time, it takes a lot of memory. So in the real world applications, you'll hardly see somebody using it. If you want to use it, they'll use its implementation of like KD trees or LSH implementations of this, and then only can you use it. You can decrease the time a bit. Is it clear? Okay, now we'll move on to some other things of this KNN. So now the problem is, you have an implementation. Now I said this K isn't have a parameter. So if you see this K over here, this K, this doesn't happen. You have to set it. Usually set it for K is equal to 3, 4, 5, 6, or whatever you have. So this is the control that you have. There are learner parameters which algorithm will learn. So there are parameters that you have to set. And now how to set this K? That's a question. Okay. Now we'll address this question. How to set hyperparameters. In our case, it's K. Again, reiterating the thing. My job here is not to teach you an algorithm. My job is to teach the revolving concept around it. These concepts will get repeated in every algorithm. But if you sort of use KNN and understand these concepts using an algorithm, it'll really be beneficial for you, because you know an algorithm and how to use this. That's why I showed you how to split the data, and then afterwards how to do the computations. Now we'll see how to set this parameter. Okay, so this concept will be repeated everywhere in every algorithm. There will be, wherever the algorithms have parameters, you'll have to set them. Okay, now we'll see its effect, how to set this K. Okay, let me make it again toy example. Let's suppose these are our points. These are emails which are not spam. Okay, and let's say these are emails which are spam. I'm just making sort of two clusters. I'll have to see which K is better. Let's suppose there is one point of blue region over here. Let's say here. Like this. I'll copy the data set because it will be heavily used. Copy. Okay. If you set, let's suppose K is equal to 1. So now you have to set you have to set K. If you say, let's say K is equal to 1, you just have to check one neighbor. Okay. So this is our query point. So if you check this over here, if you draw a point over here, so now its neighbor is red. So it will sort of say that this query point belongs to the spam emails, belongs to the red cluster. So if you again say the same thing for this point, so this will say it's a blue point because you are just checking one neighbor. Similarly, for this points which are in the vicinity, this point, similar this point, it will say it is in the blue cluster. So if you draw a surface like this, so if you check for all the points in your vicinity, you'll get a curve like this. This is the curve you'll get. Maybe I'll draw this curve with some other color. Okay. This is for k is equal to 1. This is what we call as decision surface. What does the meaning of decision surface? This means on this side of surface, every point is a blue point, or we'll say this is a not spam mail or no spam mail. And on this side of the curve, these are spam emails. Okay. This is for k is equal to 1 because it's considering k is equal to 1 and it is saying only check for the first neighbor. Okay. Now if you keep on increasing this k, okay, you see this is a non-smooth curve. If you see this is totally like unsmoothed curve. Okay, and it is trying to what we call as overfit. We'll see that what is meaning of the overfitting. So if you again take the same example, now you will see if you increase this k, if you increase the if you increase this k, now you will get more smoother curve. If you say let's suppose k is equal to 3 now. So for this point, if k is equal to 3, if there's a point for this, it will check for this one. Let's suppose we have a point near to this. So it will check for this neighbor, this neighbor, this neighbor. So it will still classify it as a blue point. Okay, blue cross. So that's why if you see, if you sort of make a classifier where k is equal 3k or k is equal 5, let's say, so this curve will become more smoother. This will become like this. So while you increase this k, if you increase to 1, 2, 3, the curve becomes more smoother if you see it. Because here it was trying very hard to get each at this point. So here you see that it was, if we had just only one neighbor, so it was considering this curve over here. Okay. So for k is equal 1, you saw a non-smooth curve. For k is equal 2 also you see some non-smooth curve. If you keep on increasing this k, the curve will become more smoother. Okay. As the k increases, the curve becomes smooth. Now we'll have to sort of find the best fit, the best decision boundary. The best decision boundary. Okay. What will happen if k is equal to n? So I'll ask you a question. If you understand, what will happen if k is equal to n? I'm saying that if k is equal to n, that is every neighbor is being checked now. Like every point in the D train is considered as neighbor. So what will happen this way? So let's suppose we have two classes. In first class we have n1 points. In second class we have n2 points. This is class 1, class 2. I'm saying that now everything is being checked. If you see the algorithm, so what will happen there is, so every point will be checked and it will basically consider the neighbor. So if n1 is greater than n2, if there are more points of class 1, so obviously the distance computed, this when distance will be computed to each and every point, then this n1 will win. Why? Because there are more number of points. So when we'll do majority vote, so obviously you'll get more labels of this. If you query a point, for example xq, you'll query a point and you will compute the distance of this point with respect to every point in the D train. So what you will feel is, you will say this, it will give n1 as label. Why? Because n1 points are more. Because k is equal to n, you have to check the distance for every point. And if n2 is greater than n1, then label will be, this is the number of points where a more is called majority class. This we call it as majority class. So I'm saying if k is equal to n, if all the points are considered as neighbors, so then this classifier will be biased towards the majority class. Whosoever class has more number of points, it will say the point belongs to that cluster. Have you understood this point?
Yes, sir.
So what am I saying is, I'm saying if we are saying k is equal to n, k is equal to n means that all the points in D train are considered as neighbors now. So in the algorithm, if you see, if you have a query point now, you give it a query and you say what's the label of this point. So it will again do compute the distance with each and every point. Then it will try to see the top k distance. Now k is equal to 1, so it will not remove anyone. So then after it will do a majority vote. After doing majority vote, it will find that then the major class wins. So the points which are more in number, that's obviously n1 here. So it will give n1 label. So here it will give n2 the label that n2 points are. It will give that label. So you see that it doesn't make any like this is like making no decision. This is just seeing the majority class. Are you seeing the effects of k? Like this can also be seen, the effects of k. How this k is deciding the decision boundary. That's the really important. How to even set this k. So I'd like to show you in the code. I think I have the code. So if you see the code here, the first thing is we're again making those, generating this some random two blocks and with the center this and this, and then I'm adding some noise also. I'm not saying that it's a perfect this where we had these two clusters which are perfectly separated. Now I'm again adding some noise. Okay, this is the noise, and now I am first saying, let's suppose k is equal to 1. Okay, that's why I'm giving the range, and I'm plotting this decision surface. So this is the code for plotting decision surface. So if I run this, so you will see this is the decision surface. K is equal to 1. So these points are clustered together. Like for example, if a point belongs anywhere here, it will be classified red. So if a point belongs anywhere here, this will be classified red. This is red point. So here, this is blue points. Again, this is red. Why is it red? Because you see one red point over here. You see again one red point over here, because but there are more number of blue points. So this territory is blue. So this is again a territory red. You see this is totally uneven surface. Okay, if I increase the number of if I say, let's suppose k is equal to, let's say k is equal to, this is k is equal to, it became a little bit smoother. So now you saw that this point is not, this is now green, again blue territory. Okay, similarly these point blue, it became a little bit smooth. So I'll plot this k from, let's suppose 1 to 10, 1 to 10. There is some problem maybe with plotting from 1 to 10. Obviously that. So you see over here, if it fits on the screen, you see, like for example, for k is equal to 1, for k is equal to 2, there is, and now it becomes smoothened. If you see over here, this is totally smoothened out. There are no these territories have been removed. That's what I'm saying, that when k increases, the surface becomes a little bit smoother. Okay, if you see over here, the surface has been become more smoother. So if I keep on increasing it, it will become more smoother. This is my decision boundary. Okay, and this is the territory that defined by different colors. Okay, which k will you choose now? That's up to you. Which k will you choose, and we'll find an ideal k where basically the accuracy is more. Okay, is it clear? What is the effect of k? So are you seeing the effect of k? This one is a terrible
Yes, sir.
case. So it is trying to like forcefully fit it everywhere. So if you see it over here, it's trying to forcefully do it when k is equal to 1. So for even here, the single point, this red single point, it is creating a red territory over here. If you see over here also, for a single point, so it was better if it considered blue and made some misclassifications, but it is not leaving any other point. So that's why if you made k is equal to 2, so it left of these derivatives, but here it still kept it. In the 3 also it did the same. But where we were increasing the value of k, it sort of made it smoother. That is the concept of like generalization. You have to generalize value. You should not overfit or underfit. Okay. So now we'll see what is the meaning of this overfitting and underfitting. Now moving back onto this, so the question is now overfitting and underfitting. So we'll keep on revisiting. This is so fundamental concept. We'll keep on probably visiting it multiple times along the tenure of this course. So we'll see what overfitting is, what underfitting is. So in this scenario, whatever we have studied so far, we have studied two cases. So if you saw that curve where we kept k is equal to 1, so there you saw a unsmoothed curve. You saw curve like this. You saw curve was going like this. It was trying very hard to consider every point should get the correct label. Like it was trying to predict every point as correct. So that's what this under overfitting means. Overfitting means, so it is it's making models so complex. So it is trying to capture every information, if that information is even noise. Okay, so if I have to formally define what is overfitting and what is underfitting, overfitting occurs when this model is too complex. If the model is too complex, so here we're okay if we had these 2 points, if they were misclassified. But now this decision boundary is making sense. For example, if this point is there, if a point is like this, so obviously this should be considered as red. But if you now ask this classifier, what is this point, it will obviously say it is a blue point, because it even captured the noise. It captured the noise and thought is the real data. So what is overfitting? So overfitting is, it happens when the model is too complex. So it captures noise also, noise or outliers, we can say. It captures noise and it gives them the weightage also. Okay, and it captures these fluctuations in the training data, and it does not capture, it tries to memorize everything, we can say. It tries to memorize. Okay, and why does it happen? It has a lot of detail why does it happen, and there is something called as low bias, high variance, and things like that. It's sensitive to small train, and then we'll keep on visiting this. But right now at this stage, consider overfitting means if a model is too complex and tries to work really hard, so that every point that is there in the training, it tries to guess its correct label. Okay, that's the meaning of overfitting. So overfitting happens when the model is too sensitive to noise. When you give it noise, it even captures it. It says, let me memorize everything, and I'll say there is 100% of accuracy on the training data now. But if I test it now, so if I test, it will be performing terribly on the test set. Because what it tried to do is, it tried to not capture relationships, rather it captured the noise also. It was working so hard to capture every point should be classified rightly. Every point should be every prediction should be made right for every point that's in the training set. It did not care about test set. So that's why I'm again coming again and again to generalization. The algorithm should be generalized. Okay, so this I can call it overfitting. So if you see, what is the underfitting? Underfitting is that k is equal to n wala problem. So there it was doing nothing. So it was being so lazy. It was saying every point belongs to majority class, whatever you say. So it was saying k is equal to n. So it was just giving a decision boundary, and it was saying whatever point you give me, it belongs to the majority class. Okay, because it was doing that, computing distances with each of the point in the retrain, and then doing the majority vote. And obviously, in the majority vote, the majority class will win, because there are more number of points for majority class. That's why this will be called as underfitting. So underfitting happened when k is equal to n. This happened when k is equal to 1. So what is underfitting? Let's define underfitting also so that you make notes. So underfitting means that when the model is too simple to capture the underlying structure, it does not capture at all. Its model is too simple. Model is too simple to capture relationships. Okay, so it does not bother at all. If you see it in the KNN, it does not try. If you give him any point, it will say it's majority class. I don't want to do anything. Okay, here in the overfitting, it was trying so hard to get every point right. So here in the underfitting, it is trying, and it is not even trying at all. The two extreme cases. So what do we want to find? We want to find best fit. Or best fit means we want to find best decision boundary. Okay, we want to find best decision boundary. Decision boundary. Okay, that's what we want to find. So based on this k, now this k will give me this. So is the overfitting underfitting at least at some intuition level clear? What is the meaning of overfitting underfitting?
Yes, sir.
Overfitting means when the model is too complex, it captures everything and tries to give nearly 100% accuracy on the train data set and performs terribly on the test. It tries to overfit the data, memorize basically everything. And underfit means if it is so simple and it does not capture any relationship with the data. It says like whatever you give me, this is it. Take it. As in this k is equal to n, it was telling everything belongs to majority class. Whatever you give me. Okay. This is sort of democracy. If you see, this is democracy. So whoever gets the more number of seats doesn't matter if he's educated, uneducated, doesn't matter. He'll rule. Okay. Here, this is sort of like a very restrictive manner where everything, even if noise, that is captured, and it does not. It memorizes everything. It does not even respect that key. Something can be noise, something can be an outlier. Okay. So we want to find a best fit. So for us, best fit would be like this. So best fit would be something like this. Okay. Something will be like this. This we'll call best fit. This is the concept of overfitting and underfitting. So overfit surfaces, they are really prone to these overfitting surfaces. They are prone to noise. This guy doesn't even care. You do everything. This guy doesn't. It is not working even. So now we have to see how to avoid this underfitting. Now, how to avoid this underfitting? How to avoid this overfitting? What to do? The question that we are addressing is how to basically set this k. That's the topic we have. How to set this hyperparameter. Now we are seeing that if k is equal to 1, it sort of underfitted it. It overfitted it. When k is equal to n, it overfitted it. Now we have to find the right k. So what I can do is, now I have this d test and d train. This is my dn. Let's suppose this is my d train data set and this is my d test. I can do like this. So what I'll do is I'll say, let's suppose I'll keep k. This is the value of k. K can be 1, 2, 3, 4 up till n. Okay. And then I'll find the test accuracy. Okay. I'll use the training set as d train everywhere. So d train is my training set everywhere. This will be training set everywhere. Now I'll compute the accuracy. Compute the test accuracy. Okay, I'll compute the test accuracy. So for example, for this one it was 0.6. For this two, let's suppose it was 0.65. For 3 it was 0.7. For 4 it was, let's suppose, 0.82, something like this. And then you will see it again started decreasing. It is again 0.6, 0.7. So you see at k is equal to 4, the curve will be like this. If we plot k onto this and if we plot accuracy, you'll get some curve like this, let's suppose. Okay, this at this point, let's suppose this is our k is equal to, say, 4. You got the highest accuracy at this. So you can set k is equal to 4. Now you are saying this k is equal to 1 to n, and you will not even go to n. Obviously, you will go to some fixed number. Let's suppose k is equal to 1 to 20 or something. So you will use retrain and you will check the test accuracy. Wherever the test accuracy was more, okay, then you will set the k as that thing. Is it clear? Is it clear?
Yes, sir.
Okay. So can I say, let's suppose I set my k is equal to, say, 4. Can I say that here you see the 0.82? Can I say that 82% is the accuracy of KNN, is the accuracy of 4NN, let's say 4NN on my d test, okay, when d train was used. So I can claim this, okay. But the problem that I'm answering is that I have to see future emails. Okay, this is not that they won't be present in the test set also. So what I have to do is I'll have to check future emails. What the emails will be coming on the future? Can I claim there is 82% accuracy on that? Can I claim this?
Yes, sir.
How many of you feel that we can claim this there is an accuracy of 82% on the future data set? How many of you feel this?
No.
Marian?
Yes, sir.
Actually,
Mm,
here this accuracy is on D test. It is not on the future data. Okay, you can claim this is on the test data, but this is not on the future data. Okay, why? Because future data you haven't seen. Here you set this k based on the D test. That means your algorithm has seen this D test when it was testing. So you set this k based on the D test because you are taking test accuracy. Okay, you can just claim that test accuracy was 82%, but I'm not sure about what will happen in the future for the unseen data. Okay, test data I'm sure that 82% accuracy is there, but what will happen to the future, because I don't know if the distribution will remain the same, if the accuracy will be high, low, nothing. So for that we'll have to see what can be seen about the unseen, what can be said about the unseen data. So here you are seeing the data. Okay, so now the question still remains, the question of generalization, it still remains there. If you understood this argument, my argument is that if you have this d and you split it into d train and d test. So on d train you are using the KNN, you are using the find nearest neighbors from NN. Then how to find k, you are using this d test because you're evaluating on d test, and then you are setting this k wherever you are getting higher accuracy, you are saying this k is there. But still I am saying that this 82% accuracy is on d test, it's not on the future data, because you haven't future data you haven't seen, but this k was set on this. So there should be some technique by the help of which I can say that the accuracy of this my model on unseen data is this much. It's not on just d test, it's on unseen data, because test set was used over here. If you see it, no longer remained unseen, because I use this k, you set this k based on this test. Is the problem clear?
Yes, sir.
So now we are we are sort of setting this k based on the test accuracy, where we are using the test data set, and we don't know what will happen to the unseen data. So if tomorrow some image will come, what will happen on those? Okay, some data we have to keep purely unseen for the model. Okay, that's where the concept of cross validation comes. Cross validation. So some data will never show to the model, we never use it anywhere. So for example, in this k nearest neighbor, I'll say I have this d train. Okay, then what I'll do is I'll have a cross validation set. Okay, and then I'll have test set. This test now I'll keep total unseen. Okay, and this cross validation I'll use for setting the k. Okay, so let's call this as whole d train with the cross validation. So what I'm saying is I'm now converting my data into three sets. I'm saying there is the training by the help of which I'll compute those nearest neighbors. How to set this k will be based on cross validation. Then how to test it, I'll consider this as my unseen data. I'll not even look at it, I'll not use this data to set k to see KNN. This is now my unseen data. This cross validation I can use it for setting the k hyperparameter k, and then I'll see, and this I'll use to compute those nearest neighbors. Is it clear? Now how to do that, there are concepts like cross validation and things like that. So simply telling you that now this dn will be split into three things. D train will be there, d cross validation will be there, and d test will be there. And by the help of this d train, what we'll do, we'll compute the nearest neighbors, and from the CV we'll compute the k, and this d test is total unseen, this is fully unseen. Okay, and this fully unseen data will be used then for the evaluation. And now for on this test set, if I got accuracy of, let's suppose, 0.8, that time I can say that now my accuracy is 0.8 on unseen data, because my this data was never used in the model anywhere. It was not used in this computing, and then it was not never used in finding this k. It was only used when I really tested it. Okay, I would like to show you a sample code of finding this right k by just using the k test and this d test, and we'll take this cross validation further in the next class. Let me show you the code. I hope my screen is visible. So here you can see it. So what I'm doing is I am making, like, again, 1,000 samples and things like that extra. This is the whole thing. So now I am saying k values is equal from ranging from 120, and now I am adding accuracies. So if I now plot these accuracies, you will see. So when I keep on changing this, so I am getting, like, from 1 to, this is the k value from 1 to 19. So you see at 12 I am getting the highest accuracy of 0.82. Okay, but this is on the D test D train, so this is not cross validation. So what I'm doing is, so here I had data like this, so this is my D train and this was my D test. So using the test I was setting the K. I was setting K. The example that we saw earlier, so we are using this D test to set the K, and for this D train we are computing the nearest neighbors. Or in order to set the K, set the value of K, so we are using this D train. So now whatever accuracy I got here, let's suppose I got the accuracy of 0.82. So what I can say about this, I can say the accuracy of this 0.8 is on the test data. This is not on unseen data because we have no longer kept it unseen. Why? Because we have set this K based on this D test. Okay, so in order to mitigate this problem, in order to sort of tackle this problem, what we did is we said we'll split our data set into three things now. We'll have D train, then D cross validation, and then D test. And we have something called as K fold cross validation that we'll see. Okay, I think if you don't have any questions, I'll stop the recording.